y'all, welcome to Ms. Clark's chemistry class. This lesson is over percent yield. Now, if you have not learned anything about stoichiometry, make sure and catch that lesson first. I am going to talk a little bit about stoichiometry so I can talk about percent yield, but if you don't know what stoichiometry is, then you've got to start there first. We talked about stoichiometry being the math that you use to adjust your chemical equation, your chemical recipe. Like if we were making cookies, remember we had this conversation before. If we were making cookies, our recipe only makes 2 dozen. I need to make 500 dozen. That doesn't mean my recipe's bad. I just have to adjust it and do some math. That math that you do to adjust recipes in chemistry is called stoichiometry. So if you have a chemical reaction and it tells you that this is the chemical reaction that you use to make 12 moles of carbon dioxide, we can still use that same chemical equation to figure out how to make 555 moles of carbon dioxide. And the math we would use to figure that out is called stoichiometry. Now, stoichiometry is always going to tell you your theoretical yield. How much product would we produce in a perfect world? Math is always going to give us the answer for the perfect world solution. If we were really doing a chemical reaction in the lab, it's not a perfect situation. Lots of human errors that we could make in the actual lab. So when you're doing a chemical reaction and you get the product that's produced and you weigh it on a scale, it's never going to be the exact same amount as that theoretical yield. Again, because theoretical yield is with math. Math never allows for human error. When we're actually in the lab doing the experiment, our human selves, we're going to make error. So we're going to need a formula. Go get your notes, get a periodic table, get a calculator. Let's get started. Now, to calculate percent yield, we are first going to have to do a stoichiometry problem. The very first step, stoichiometry, balancing the chemical reaction. So let's balance this chemical equation here. I'm going to go ahead and use the tally mark method. Okay, so we've got magnesium, we've got one of those. We've got hydrogen, one of those. Let me see. Nitrate stays together on both sides, so I'm going to leave that together, nitrate. And I only have one of those. On the other side, magnesium, 1. Nitrate, I have 2. And hydrogen, I have 2. So magnesium, I'm not going to start there. I'm going to start with hydrogen. I need to put a 2 here. That's going to give me 2 hydrogens and 2 nitrates. I'm going to go fix my nitrates. Oh, already fixed. That is all I needed was that 2. So now that my chemical equation is balanced, let's start the actual problem. Okay, so let's read this question. If I start this reaction with 40 grams of magnesium and an excess of nitric acid, how many grams of hydrogen gas will I produce? Okay, so we're looking for how many grams of hydrogen. So we're looking for how many grams of hydrogen. We're starting with 40 grams of magnesium. So we're starting with magnesium. When we solve this, this is going to be called the theoretical yield. Your theoretical yield is always the answer of a stoichiometry problem where you're solving for how much product is produced. Because we are figuring out how many grams of product. So let's start our problem. We're going to start with 40 grams of magnesium. What's on top comes on bottom. Grams of magnesium. Molar mass is equal to 1 mole of magnesium. Our grams are going to cancel out. Whatever is on top comes on bottom. Moles of magnesium. The very first time you put mole on bottom, we're going to put mole on top, and we're going to change to our new compound. We're solving for hydrogen. We're solving for grams of hydrogen. Right now we have moles of hydrogen on top, so we need one more step. So I'm going to bring that down. 1 mole of hydrogen is equal to the molar mass of hydrogen. Okay, so let's put these masses in and our mole ratio in. First, let's start with our mole ratio. Remember, the mole ratio is the step where we have mole on top of mole. This is where we're going to go to our chemical equation and put our mole ratios. There's no number here for H2. That's going to tell us it's a 1. So I'm going to put a 1 there. Magnesium also. There is no number in front of magnesium, so the mole ratio for magnesium is also a 1. Let's look at our grams. This is our mass from our periodic table. If we had our periodic table in front of us and look at magnesium, we would see that its mass is 24.301, I think. I hope that's right. The mass for hydrogen is 1.008, but we have two hydrogens, so that's going to be 2.016. Okay, we've got everything ready. All of our units cancel out. We're ending with grams of hydrogen. I'm going to put this in the calculator. Now, I put this in the calculator a little bit different than other people. I start at the beginning, 40, and I just go from left to right, top to bottom. So I'm going to move over. The next number is on bottom, so I'm going to divide 24.301. The next number, now see these numbers, ones, I don't include ones because ones do not change the math. So our next number, this number is on top, so I'm going to multiply times 2.016 equals, because that's all the numbers that we have. The grams of hydrogen gas that we will produce, I am getting 3.3 grams of hydrogen gas. For percent yield, I would call this my theoretical yield. Math is telling me I should be able to produce 3.3 grams of hydrogen gas if I start with 40 grams of magnesium. Of course, that is with no human error, no measuring errors, no errors at all. Perfect world. That's why this is called the theoretical yield. Here is where we get to the percent yield. This is the new part. I know, right? We're like how many minutes into this lesson and I'm just now teaching you the brand new stuff? Sorry, y'all, but that's how it goes sometimes. If 1.7 grams of hydrogen is actually produced, what was my percent yield of hydrogen? Now remember, math said we should be able to produce 3.3 grams of hydrogen gas, and I called this the theoretical yield. This problem is telling us 1.7 grams of hydrogen is actually produced. We call this the actual yield. Now, percent yield does have a formula. Let's write that down. Percent yield is just going to be dividing. It is going to be your actual yield over your theoretical yield. That's going to give you a decimal. We need a percent, so then you can multiply that by 100. Actual yield divided by theoretical yield times 100. Okay, let's see what that looks like. Okay, I brought all that information over to a little bit more of a clean area for us. So percent yield is actual yield, 1.7, divided by our theoretical yield, 3.3. This is going to give us a decimal. You can just move that decimal over twice to get a percent, or you can multiply by 100 to get that percent. I'm going to go ahead and multiply by 100 because it just is a little bit easier sometime. Our percent yield is 51.5%. That does not sound like a very good percent yield to me. That seems like a lot of waste. Let's try another example. Okay, I have a new chemical equation. It says if 25 grams of carbon dioxide is produced in this reaction, how many grams of sodium hydroxide should be produced? Again, if we're figuring out the mass of what should be produced, another word for this is called theoretical yield. And since we're going to have to do stoichiometry to figure this out, let's start by balancing the chemical equation. Dang y'all, look at that. It's already balanced. It happens. Okay, let's work this problem. Ones in all of the spots. I'm going to erase this balancing tally marks to give us a little bit more space to work. So let's start with our given. So if we have 25 grams of carbon dioxide, this is produced. That is a product, but that's okay. You can use a product to figure out how many other products are produced. Don't let that freak you out. It's okay that we're going from product to product. How many grams of sodium hydroxide should we produce? Grams is on top, grams goes on bottom of carbon dioxide. Grams is the molar mass. That's the mass of 1 mole carbon dioxide. What's on top comes on bottom. This is the very first time we're putting mole on bottom. So we're going to put mole on top, and we're going to change to our compound that is in our question, sodium hydroxide. Now, if we were solving for moles of sodium hydroxide, we would be done, but we're looking for grams, so we need to go one more step. So whatever is on top comes on bottom, moles of NaOH, Now we're ready for grams of NaOH. Since this is the molar mass, that's 1 mole equals the mass. Let's fill in all of our blanks. Now the easiest blank to fill in is our mole ratio because this equation was already balanced, so all of that is just going to be a 1. Now we need to add the molar mass up of carbon dioxide. So I've got the mass of carbon, 12.011, plus the mass of 2 oxygens. I use 15.999 for oxygen. And I am getting 44.009 as my molar mass of carbon dioxide. Now I need to find the molar mass of sodium hydroxide. Sodium, 22.99, plus an oxygen, 15.999, plus a hydrogen, 1.008, equals, and I am getting 39.997. Okay, I'm going to put this in the calculator. Again, I do this a little bit differently. I go from left to right, top to bottom. 25 divided by 44.009 times 39.997. Again, I ignore all the ones because ones don't affect my math. So if we have 25 grams of carbon dioxide, we should also have 23 grams of sodium hydroxide. If 50 grams of sodium hydroxide are actually produced, what was my percent yield? So remember, percent yield is actual yield. That's the number given to you in the problem. That will always be given to you in the problem, or you will do it in the lab and actually measure the amount of product produced. If you're in my class, we will be doing this. So actual divided by theoretical. Remember, theoretical, that's your math. That's your stoichiometry. Let's multiply that by 100 to get a percent. So our actual yield, that's 50 grams. That seems like a lot when we only got 23 grams times 100. This doesn't seem like we're going to have done a very good job on this one either. 50 divided by 23 times 100 equals, 217%? What? Y'all, that's not a very good problem. But at this point, I really want to be more concerned with how to do the math than was that really the best example to work? I'll admit it wasn't, but we got to practice the math. Hey, quick little tip. If a teacher is ever asking you for the theoretical yield, that just means you're solving stoichiometry problem. Solve that for the product produced. That is your theoretical yield. Remember, the only way to be successful at stoichiometry percent yield, practice, practice, practice. I do have a video where I just work lots and lots of practice problems. If you're needing help, make sure and check that out. Until next time, bye y'all.